You call a function. It runs. It finishes. Its local variables should be garbage collected. Gone. Dead. But then you call the object it returned, and it still remembers those variables. How? I am Ahaz. Today, in episode 30, Closures and Scope Deep Dive, you will finally understand one of the most misunderstood features in all of Python. This is the secret behind every decorator you have ever used, every callback in an async framework, and every factory function in NumPy, Flask, and PyTorch. We will cover the LEGB scope rule, how Python finds any name in your code, the nonlocal keyword to modify enclosing scope variables, what a closure actually is at the memory level, factory functions that generate specialized functions at runtime, the loop closure trap that destroys 90% of beginners, closure versus class, when to use each one, and real production patterns. Stay until the memory diagram. It will change how you see Python forever. Let's go. Every time Python sees a name, it searches for scopes in a fixed order. This is the LEGB rule. Local scope. The inside of the current function. Python looks here first. Enclosing scope. If the current function is nested inside another function, Python looks in the enclosing function's local scope next. This is where closures live. Global scope. The module level. Variables defined at the top of your file. Built-in scope. Python's built-in names. Len, print, range, type. Python always searches in this order. L then, E then, G then B. If it finds a name in local, it stops. If not found anywhere, name error. This rule explains every confusing variable behavior you have ever seen in Python. A local variable shadows a global with the same name. A nested function can read from its enclosing function. LEGB is the map to every scope question in Python. Let's see local and global scope with live code. Look at the code. At the top, we define x equals 10. This is global scope. We define a function called show. Inside show, we define x equals 99. This is local scope. Inside show, we print x. Python finds x in local first and prints 99. Outside show, we print x again. Now Python finds a global x and prints 10. The local x inside show did not touch the global x. They are completely separate objects in separate namespaces. Now look at the global keyword. We define increment. It uses the global keyword to reach up and modify the global count. Without the global keyword, Python would create a new local count. The assignment would never touch the module level variable. Rule of thumb. Reading a global variable works without any keyword. Modifying a global variable requires the global keyword. But in professional code, avoid global mutation. It creates hidden dependencies and makes functions impure. Use return values and closures instead. The E in LEGB, enclosing scope, is the most interesting one. It only exists when a function is defined inside another function. Look at the code. We define outer. Inside outer, we define x equals 10. Inside outer, we define inner. Inner prints x. It finds x in the enclosing scope of outer. This is a read. No keyword needed. Now we want inner to modify x. Without nonlocal, Python creates a brand new local x inside inner. The outer x is untouched. Look at the right side with nonlocal. We add nonlocal x inside inner. Now, when inner assigns x equals x plus 1, it reaches into the enclosing scope and modifies outer's x directly. After calling inner twice, outer's x is 12. The rule, reading enclosing variables, free, no keyword. Modifying enclosing variables requires nonlocal. This is exactly how closures maintain state. This is the heart of every counter, accumulator, and memoizer you will ever build. Now we can define a closure precisely. A closure is an inner function that captures and remembers variables from its enclosing scope, even after the enclosing function has returned and its stack frame is gone. Look at the code. We define make_counter. Inside we define count equals 0. Inside we define increment. It uses nonlocal count, increments, and returns count. Make_counter returns increment. the inner function. Now we call make underscore counter and store the result in counter. Make underscore counter's stack frame is gone. Count should be dead. But when we call counter, it returns 1, 2, 3. The variable count is still alive. Python kept alive because increment captured it. We can make two independent counters, counter A and counter B. Each has its own separate count variable. They do not share state. That is the power of closures. Each call to make underscore counter creates a completely isolated memory environment. Let's look inside the closure at the memory level. Python stores captured variables in special objects called cells. Every closure has a dunder closure attribute, a tuple of cell objects. Each cell has a cell underscore contents attribute, the actual value. Look at the code. We define make underscore adder. It takes n and returns an inner function that adds n to x. We create add5 by calling make underscore adder with 5. Now we inspect add5. Add5 at dunder closure is a tuple with one cell. Add5.dunder closure index 0. Cell underscore contents is 5. That is n, captured and alive inside the cell object. We can also inspect dundercode.co underscore freevars. This gives us a tuple of the names of all captured variables. For add5, it returns the string n. This is the exact memory mechanism that keeps closures alive. Python's garbage collector will not free a cell as long as any closure hold a reference to it. Understanding this tells you exactly why closures have no memory leak risk as long as you do not store them indefinitely. Factory functions are the most practical use of closures. A factory function returns a specialized function configured at creation time. Look at make underscore multiplier. It takes factor and returns a closure that multiplies any input by factor. Double equals make underscore multiplier of 2. Triple equals make underscore multiplier of 3. Now double of 5 gives 10. Triple of 5 gives 15. We created two specialized functions from one template. This is more flexible than a class and less verbose. Look at make underscore validator. It takes min underscore val and max underscore val. It returns a closure that checks whether a value is in range. We create validate underscore age and validate underscore score. Each carries its own min and max. Now look at make underscore power. We use it to create square, cube, and fourth underscore power. Each is a one-argument function. This pattern is called partial application, fixing some arguments of a function to create a simpler version. You will use this constantly when building ML pre-processing pipelines. The loop closure trap destroys 90% of beginners. This is the most common closure bug in all of Python. Look at the left side, the broken version. We loop from 0 to 3 and create a lambda that returns I for each iteration. We store the lambdas in a list called functions. After the loop, I equals 2, the last value. When we call any function in the list, it returns 2. Every single one returns 2. Why? All three lambdas capture the same variable I, not the value of I at creation time, the variable itself. By the time we call them, I is 2 and stays 2. Now look at the right side, 3 correct fixes. Fix 1, default argument. Def f of I equals, I captures the current value by binding it as a default. Default arguments are evaluated at function definition time. Fix 2, use a factory function. Make underscore func captures I in a new enclosing scope per iteration. Each call creates a fresh cell with the current value. Fix 3, list comprehension with default argument lambda. All three fixes work. The factory function approach is the cleanest and most Pythonic. Memorize this trap. You'll see it in code review every week. Closures and classes can both hold state. When do you choose one over the other? Look at the counter example implemented both ways. The closure version is 8 lines. The class version is 12 lines. The closure wins on brevity. It is a pure function that happens to hold state. But now I want to add a reset method and a get method. The closure needs nested function definitions for every method. It gets messy. The class adds methods naturally. Here is the rule. Use a closure when 1 callable, simple state, throwaway, or one-off. Use a class when multiple methods, complex state, inheritance needed, where the object will be passed around and inspected. In practice, closures for callbacks, decorators, and factory functions. Classes for data models, services, and anything with a life cycle. A class with only dunder init and dunder call is usually better as a closure. A closure with more than 3 inner functions is usually better as a class. 3 production closure patterns you will use constantly. Pattern 1, memoize. The simplest hand-rolled cache decorator. The closure captures a dict called cache. Before calling the function, check if the args are already in cache. If yes, return from cache instantly. If no, compute, store, return. Each decorated function gets its own isolated cache dict. Pattern 2, counter with reset. We use nonlocal to maintain counter-cross calls. We return a tuple of 2 functions, increment and reset. Both share the same count cell. Calling increment adds 1. Calling reset zeros it. This is the publisher-subscriber pattern in miniature. Pattern 3, partial application. We implement our own functools.partial using a closure. Locked_args and locked_chords are captured. The return wrapper prepends them to every call. All 3 patterns are used in real frameworks. Flask uses memoize for route caching. Django uses partial for URL resolvers. Essentio uses counter closures for task tracking. Our mini project, a configurable event handler system. This is a pattern used in every GUI toolkit, game engine, and web framework. Look at the code. We define make_event_handler. It takes an event_name and optional middleware functions. Inside, we define a list called handlers. We return 3 closures: on, emit, and off. On takes a handler function and appends it to the list. Emit takes *args and *chords. It runs each middleware first for logging, validation, or transformation. Then it calls each registered handler with the process data. Off removes a handler from a list. All 3 closures share the same handler's list and event_name. We create 2 independent event channels, click_handler and keypress_handler. Each has completely isolated state. We register handlers using the on function. We fire events using emit. This is closures, nonlocal, factory functions, and *args all working together in a real system. This exact pattern powers React hooks, Vue's composition API, and Python's Essentio event system. Your challenge: build a closure toolkit. Step 1, write once_only. A closure decorator that ensures a function can only be called once. Every call after the first returns the cached result immediately. Step 2, write make_accumulator. A factory function that returns a closure. Each call adds the argument to a running total and returns the new total. Reset it with a separate return function. Step 3, fix this broken loop. You're given a list comprehension that creates closures over a loop variable. All closures return the same value. Fix it 3 different ways. Step 4, implement make_pipeline. A factory that accepts any number of functions and returns a closure. The closure pipes its input through each function in sequence. Step 5, add type hints to all 4. Run mypy-strict. 0 errors required. Paste your solution and mypy output in the comments. I read every single one. Let's recap what you learned today. LEGB, local, enclosing, global, built-in, the fixed search order for every name. Global keyword, required to assign to a global variable from inside a function. Non-local keyword, required to assign to an enclosing variable from a nested function. A closure is an inner function that captures variables from its enclosing scope even after that scope is returned. Python stores captured variables in cell objects accessible via dunder closure. Factory functions use closures to generate specialized callables at runtime. The loop closure trap. All lambdas capture the same variable. Fix with default args or factory. Closure versus class. One callable with simple state, closure. Multiple methods or complex lifecycle, class. Real patterns, memoize, counter with reset, partial application. Mini project, event handler system with on, emit, off closures. Next episode, functional tools, map, filter, zip, enumerate, lambda, functools.partial, and reduce. Subscribe so you do not miss it. See you tomorrow. Closures mastered. Python's memory is no longer a mystery. You now understand the foundation of every decorator, callback, and factory function in the language. Subscribe for the next episode. Drop your closure toolkit in the comments. I am Memoize. See you in episode 31.